In this lecture, uh, this name, which is rectilinear motion, will be discussed in this particular lecture. We have some topics that are important for this, as well as we will see derivation, substitutions, numericals you can say, as a practice. First of all, in this part, our whole focus, our complete concentration, I think should be on concept and derivation. As you know, derivation provides logic, reason. Concepts provides what? Clarity. What is a statement of a particular person? That is what we get from concept, from words, from a statement. First of all, you have to be clear. Is that only we will say concept plus the derivation. Two things. Two things. And what are those things that we are avoiding? We are avoiding which are numericals and numericals based on equation that comes from derivation. So these two things, it's not two things but one, which is numerical. But remember, ignoring numericals based on equation, we will be able to face challenges. Okay, so let's start. Name of this lecture is rectilinear motion. From word, this rectilinear, it says that there is a motion of a particle. Rectilinear means there is a motion of a particle. As you know, motion word is added with a rectilinear. So that's why you and I can say that body is moving. It will be moving with some velocity or constant velocity or with acceleration. But yeah, anyhow, the body is moving. The body is moving. So rectilinear word is added, which means that body is moving, but in one direction, but along one axis, and that axis can be x or y or z axis, but it does not take two axes or three axes, but only one axis. Okay, axis can be like this: horizontally, completely horizontal, completely vertical. And this is not, as you know, this is not a horizontal, complete horizontal or complete vertical, but it is a still one axis. One axis. So we can consider this as a one axis where particle can be moved. So this type of motion is nothing but rectilinear motion. Rectilinear motion. Let's move ahead. Ahead a word. I have PPT. I read it so that we can't escape any topics or main words. So as you know, motion can be divided into three parts. First is one dimension, second is a two dimension, and third is a three dimension. From one dimension we understand yes, body is moving in one direction. From two dimension we understand that yes, body is moving in two direction. It's a very easy to understand, yeah. So from three dimension you just understand yes, the body is moving along, or you can say the body is covering three axes. Am I right? Or in other words, you can say the object is going in three axes. Whatever. This was very simple about one dimension, two dimension, three dimension. We are able to move. Examples. Here, I am moving like this. Am I covering two dimension, two axis, two axis? Answer is no. Only I am moving horizontally, not vertically. Not vertically. not a body. So this was one example, and example for two dimension. Let's just say there is a object and it is going like this. So here you can see what is happening. You can see this is the x-axis, this is the y-axis, and this is our object. What is happening? This object is going like this. But here, one thing which is clear, one thing which is crystal clear, is that it is not going along x-axis completely, as well as it is not going completely y-axis. Yes or no? Yes. Means it is going also x-axis as well as y-axis. That is what is happening. So this type of a phenomena, or you can say this type of a motion, is known as nothing but two dimension, where object is governed two direction. Two direction, this x-axis and y-axis. Okay, enough. And three dimension. Here you will see we have a volume. Object would have what volume. So object like me, I am going like this. So here I am in what? I am in a three dimension. I hope you have understood. Now next, rest and motion. Rest and motion. Rest and motion. Rest is one word and motion is another word. In this subject, meaning of rest is nothing but whatever we know about rest in our normal life. This same definition of rest exists in this subject. So we say yes, there is a body. I am also body, but I am not example for rest. This board is let's consider this board as an example. What is happening with this board? Can you tell me, is it in a rest? Final answer would be yes. This board is in a rest. So you can say yes. This is known as rest. But standard definition of a rest in this subject, what would be this? So standard would be nothing but any object, whatever object you are taking, if that object is moving with time, that object is changing its position with respect to time, then you can say yes, this body is not in, or you can say at rest, because its position is changing. But what if just opposite of it? Then you would say yes, object is at rest. Means body is not changing its position with respect to time. Clear? So I hope you have understood about the rest and motion. One more time. Rest means any body which is not changing its position with respect to time is known as rest. But what about motion? Motion means any body which is moving. It means it is moving with respect to time. So this is known as our motion. Okay, it's enough. Now next, one point that we need to remember for this part and for another part which will be linked to each other in this subject. So next to note is, or you can say on, rest and motion are relative. Both are relative. They are not absolute. Okay. How are they relative? They say that I need what? Any object which is moving or at rest, they need what? They need a frame of reference, or you can say observer. Both are different, but not completely. Frame of reference. First of all, we are talking about they relative or absolute. Yeah, we are crystal clear that rest and motion are not going to be absolute. They are not absolute. Okay, but relative, but relative. Now try to understand relative motion. Relative rest means according to me, another object is moving or at rest. According to me. So who will decide? I will decide. I will decide that yes, that person is not moving. It means that person is at rest. So I am deciding, not other person. So I will be what observer, or you can say I will be frame of reference. Observer can be third person. That third person would say yes, according to you, the vehicle is so moving. According to you, the vehicle is moving. So observer is also a object, an observed you can say, and reference point is also object for this part. So remember, rest and motion are going to be relative but not absolute. But not absolute. That's why it is said that rest and motion depends on the frame of reference. On the frame of reference. But when it comes to force, so we have a separate part for the force. Does force depend upon what frame of reference? This is question. I will answer this question when we will be taking a lecture of force. Then I will answer that at that time. Now next point, there is no meaning of absolute for rest as well as for motion. An object can be both at rest or in motion simultaneously for different observer. Yeah, we see there is an object who is saying it is also moving, it is at rest. So it's all about, I think, we will decide it's all about observer, it's all about frame of reference. Yeah, according to observer, object can be moving. According to observer, object can be at rest. Yeah, that's why we can't say that both are absolute. No, both are not absolute. They don't provide exact answer. Answer can be different. Answer can be different. That's why they are relative. Frame of reference means it is a reference, or you can say it is a object with respect to position of another object. Okay. Which position of a particle is defined with respect to frame of reference. If not specified, means if a question is not providing, question is saying we are not providing what reference point, or you can say frame of reference. In that case, we will consider ground as a reference point, or you can say surface of the earth. We will consider that as a reference point if question is not providing frame of reference. Then okay. Now let's talk about next point, which is distance. Then we will say displacement, velocity, acceleration, and equation of motion. Then motion under gravity. More. First of all, let's select. This is nothing but it's a actual length, or you can say actual distance, actual path covered by any object. Here you don't ignore anything for length. Means you don't need to ignore length. For example, in a city there is a vehicle who is moving. So that for that vehicle, a street will matter. If you are finding distance, street will matter if that vehicle is going into a street. That's why. So actual path will matter. Don't ignore actual path. Don't take initial and final location of the particle for distance. Okay. It does not care about initial and final distance. Okay. Next point, if no, okay, actual length of path. Okay. Which type of a quantity distance is answer is a scalar quantity. When we say it is a scalar quantity, it means this is not going to provide the direction. This is what is meaning of a scalar. Yeah, magnitude will be there. Magnitude will be there. When we say vector, we see yeah, magnitude is there. When we say scalar, yes, magnitude is there. But it's all about a direction between them. So remember, scalar does not provide a direction. Next we have can't be negative. Who can't be negative? Distance. Yeah, if it is a zero, there is no sense. Zero means zero, nothing. But can't be negative means distance will not be always negative. Even in our real life, you can see, observe carefully, then you will see, yes, it is not negative. Unit will be better because length, as a unit of length matter, So, okay. Let's draw a figure so that we can get more clarity about distance and displacement. This is a diagram. This is A point, B point. Initial location, you can say initial location, name of this is A, and final location, which name is B. There are three paths. First, like this curve, direct curve, and third, which is a zigzag curve, like this. This is our one path, second road, or third street. This is not a street, but yeah, you can consider it as a street. Now, what is it is saying that there was a object who covered this much distance, and this same object covered from here to till here, but it went through this path. Okay. In third case, the same object went at the same location, but you can see road is different. That is what is happening in this figure. That is what is happening. So here you can see distance. This A to B, this curve is also distance. This AB is also distance, and this zigzag curve is also distance. Okay, you will see at which I will tell you. Let's say displacement. Look, it only care about initial and location. It depends on initial and final. Initial and final location. Initial location of the particle is this, and final location of the particle is this. That's it, nothing else. You don't need care about actual path for the displacement. Are you understanding? You don't need to care about actual path for the displacement, but you need to care about actual path for the displacement, not for the distance, not for the displacement. This is what is the difference between them. But we are understanding what is the actual meaning of displacement. So remember, it is nothing but sortation. So tell me, location is the same, but in this line, which one line is providing shortest distance? Answer will be second line. Second line is providing shortest distance, and this is what is our displacement in this figure. Okay, second will be. If you say this third curve will be displacement, it means you are wrong. Because only we take a straight line, not zigzag, not curve. Only a straight line. Okay. Straight line. Remember, it is a vector quantity. This is a vector quantity because it cares about the direction. That's why this is considered as a vector quantity. Next we have its direction is from initial to final. Yeah, I have told you. Next, can be positive, can be negative, can be zero. How can it be zero? Let me explain. Let's suppose you were over here, U over U. And then you went, or you can say you covered 5 kilometer distance, 5 kilometer distance, like this. But again, you reached at the same location, or you can say in your home. So now you can see where is your straight path. In this example, are you getting straight path, straight line? Answer is no. This is not a straight, it's a closed. So whenever you are observing closed curve, circle, or you can say curved line, it means displacement is going to be zero. Displacement is going to be zero. So closed, remember, closed curve, closed curve, and curve, curve can be zigzag, it can be simple. So remember, this closed curve will provide a zero displacement anyhow. And if you want to say logic is it is starting from initial point, but when it comes to reach point, then it reached where? At the same location, at the same. So initial and final is the same. That's why displacement is zero. It's a logic. This is logic. Clear? Okay. Next, some points. Relation between them. Relation between displacement. And here I am applying this mode, and this is a magnitude, or you can say direction. Try to understand. What is it explaining? This is saying displacement, this distance can be equal to displacement. Here, AB is also this second. Look at this second line. AB is also distance and is also displacement. But this first curve, AB, this first curve is not the displacement. So that's why sometimes distance will be equal to displacement, but not all the times. So it is saying distance could be equal to displacement. Remember. Otherwise, it will be greater. Distance will be greater, but displacement will be less. It would be less, or it can be equal to displacement. This is what it's a fact. Now next distance upon displacement. Try to understand. When we use this mode, it means we are ignoring what? We are moving minus sign and direction. This is what is the use of mode. Okay. So this mode of displacement. Now look at this thing, this part, not this part. It is a distance upon displacement. You know from the basics classes, you know that if a denominator is more, and not denominator is less and the denominator is more, then what happens? For example, 2 by 5. Here you can see 2 by 5. Everyone can observe that 5 is greater, which is in denominator. But when it comes to 2, which is a present in numerator, it's a less than denominator. Am I right? So what is the focus on this? Focus is if you solve this, you will get in decimal. But will it provide a number which will be greater than 1? Answer is no. This will be, this 2 by 5 will be less than 1. Am I right? Am I right? Means let's suppose 0.5. So one is which one is greater? Answer is 1. So anyhow, if one condition is only if a denominator is greater and numerator is smaller, then anyhow you will get uh, a number which will be less than 1. Less than 1. Or you can say between 0 and 1. Just opposite of it means if you increase denominator, I know numerator, or you can say another word, if a denominator is not if a denominator is less and numerator is greater, in that case we will get a number which will be greater than 1. So same thing is happening over here. Here it is saying that fraction of a distance upon displacement will give us it will be more than, it can be more than 1, or it will be equal to 1. Here distance upon distance, this is what is happening. This is what is happening. If both are same, answer would be 1. If a distance is greater but a displacement is less, then what will you observe? You will observe that yes, answer is going to be more. For example, 5 upon 2. Here 2 is a denominator which is less, 5 is a numerator which is more. When it will be simplified, answer will be greater than 1. Answer will be greater than 1. Same over here. Here it is saying if both are not same, it means displacement is going to be small and distance is going to be greater. When it will be simplified, of course, there will be a number which will be greater than 1. That is what is the whole thing in this part. Now next thing, let's write. Just opposite it. Displacement upon distance. And just opposite. I think you have understood. Yeah. Should I explain again for this? Here you can see either both would be same, or displacement would be less, or distance would be greater. For example, this is 5 and this is also 5. So 5 will cut to each other, and at the end we will get 1. So here you can see this is sign which is about equal. So both will be equal if both are same. This is displacement and distance. If both are same, then answer will be 1. But what about this sign, which is saying that this is going to be a small? It means you can see if both are not same. If they are not same, then here either, for example, displacement is so distance is greater. Let's just say this is a 6. This is 6. When you will simplify this, anyhow you will get a number which will be between 0 and 1. That is what it will happen. Fact is what? Fact is, if denominator is greater and denominator is less, then number will be between 0 and 1. If numerator is greater and denominator is less, then our value will be more than 1. That is what is fact. But you have to remember this point. Fourth trick, yeah. It depends on you. It's your choice. Now next move ahead of it. Next we have next. Next which is displacement vector. How to write any displacement into vector form. That is what we are going to see. So in terms of position vector, position vector. To visualize it, we draw a Cartesian plane. Cartesian plane. This is our y and it's a x. This is x and this is y and this is our z. Remember, this x, y, z is written for the Cartesian, but when it comes to vector, we replace them into what? Into I cap, z cap. I hope you remember this thing. When it comes to vector, then just we need to replace this x, y, z coordinates by I, z, k. Okay. Now there is a body. There is a body whose location is this in this Cartesian plane, and it displaced how much? This much. That is what we have to calculate. We have to calculate how much it displaced. This is what we have to calculate. And remember, all the conditions are given in Cartesian plane. That is main point for this question. It's not question, but concept. So initial location of the particle was this, which is A. And here we take help of what? Position vector. Position vector means it is a vector, and here this is vector. We take location of this particle from origin of the Cartesian plane. So this is our origin line. We are defining its a position. Okay. So this is our first position vector. Can I call it as a R1 vector? Yeah, you can call it. Now, here you can see second vector, which is a B. And from origin, we can draw like this. This is our second position vector, R2. And main thing is to calculate this displacement. Am I correct? So which formula are we going to apply? Let's see. I think derivation will come into picture here. So you have now that yes, this thing is what is to calculate, and our complete focus will be on this part. And let's calculate this R. Yeah, it is AB. AB is nothing but displacement. We were able to calculate displacement when there was no vector, but where there is a vector, you don't think that it's a very we will apply a simple algebra addition. No, it's a different completely. When it comes to completely different, here we will have some rules so that we can add any vector effectively. Okay. So according to triangle of vector addition, here if I remove this y, x and z, are you getting only this part which is looking like a triangle? Am I correct? That's why it is called triangle. Here we can apply triangle law of vector addition because it's a making triangle. That's why it's a making triangle. What if it was making a quadrilateral? Then we apply what? Polygon law or parallelogram law. Yeah, parallelogram law. But right now this is a triangle. So according to triangle of vector addition, initial position vector, initial position vector, which is this. So you can call in the coordinates of this a vector will be what? X1, y1 and z1. These are coordinates of a vector, and coordinates of a b vector will be x2, y2 and z2. Am I correct? x2, y2, z2. When it comes to displacement, we know final minus initial. So final is what? x2 minus x1, y2 minus y1, z2 minus z1. That is how we calculate displacement. Okay, that is. So our initial position vector is what? R1. So you know that x is along I cap and y is along z cap and z is along k cap. So that therefore this x1 can be written with I cap, y1 z cap plus z1 k cap, and our second, which is the final position vector, which is R2. So here coordinates are x2, and this I cap is used for direction, you know. So this y2 z cap plus z2 k cap, z2 k cap. Am I correct? So we go to two position vector from this figure. Either you can say R1 plus AB is equal to R2. You can say R1 plus AB, and this is, we are considering this side as a hypotenuse. So let's say sum of these two lengths will be equal to hypotenuse. So R2. Am I correct? And since we have to calculate this displacement, hence R2 minus R1, or you can say AB. So R2 minus R1. This is our a small derivation. It's our a small derivation, which is not rocket science. So R2 minus R1 is providing what? Displacement. This a small formula we will use over here. Let's apply. So x2 minus x1, this is along I cap, plus y2 minus y1, this is along j cap, and z2 minus z1, this is along k cap. Am I correct? So finally, the last formula for the displacement of two position vectors, which is given in Cartesian plan, will be used this. Okay. Okay, now next thing. Look, in this lecture I am just taking some topics that are difficult for some people. I think here is where I need to explain carefully, and that's why it will be for this lecture will be for this carefully part, that part where attention of the audience and me should be on that thing more. So after this was compulsory, where people do not understand carefully, their attention, I hope it is done. Okay, it's for average speed. Case number 1. Case number 1. If particles, not particles, if a particle travels s1 distance, s2 distance, and like that till the sn distance in time, let me write. If particle travels s1, s2 till the sn distances in time t1, in time t1, t2 till the tn, okay, respectively. In that case, in that situation, what will be our average speed? Three types of cases we will get when numericals are coming. Then this three types of cases we will face. So that's why it is compulsory to observe what kind of average speed will we get. So case number 1 is if a particle is traveling same distance, not same distance, but a different distance in different time. Means over here distance is changing, time is also changing. Time is also changing. In that case, our average speed will be equal to, remember, simple basic formula for average speed you all of us know, which is distance upon time. So distance is how much? This much. So you just need to write all this by adding addition. So S1, this total S2, total till the Sn. Am I right? Upon time. So time is also given. T1 plus T2 plus T3 till the Tn. Here you know value of a T1 will be something else, value of a T2 I think it would be something else. That's why rather than writing T1 plus T2 plus T3 is equal to T, no, they are separately, not the same. So this one thing we will get. This just you need to add all distance, just to sum up all these distances and sum up a time. Then you know distance upon time. That's it. Next case number second. Case number second. If a particle travels s1, s2 till the sn with her speeds v1, v2 till the, look at it. Time is not given. In the second case, time is not given. Now, how to calculate time? If a distance is given and a speed is given, then it's very simple. From basic formula, time can be calculated. From basic formula, time can be calculated if question is not provided. But you can see these two terms are being provided in this case. That's why it became possible to calculate this time. So for this average speed, I think it is going to different from the previous case. So total distance. This is total distance. Just sum up this S1, S2 till the Sn. And the total time. Remember, it's not average. Okay, this speed is not average. So you know T1. What is the T1, T2, T3? That is what over here you have to calculate. So how will it come? You know, T from this part T will be equal to T upon S. Am I correct? So S is a V1. For T1, S is how much? First of all, T is S1 upon S is a V1. Same with T2. S2 V2 same similar with T3 S3 V3. Am I correct? Then you will simplify so that final where the equation cannot be simplified, that at that point you have to reach. You have to reach at that point. Look at here. So finally T1 is nothing but S1 upon V1 plus S2 upon V2 plus S3 upon V3. That is how it will be continued till the Sn upon Vn. But question will be providing two distances, two times, two velocities. You can just write two distance and two times. Then simplify. Since you know it is going till the infinity, that's why till here this is enough. You don't need to simplify further it. So this was case number second. This was case number second. Now let's see case number third. Case number third. If a particle travels with a speed v1 v2 till the v in time interval t1 t2 till the t. In that case, what should be average speed? It's very simple. Since you have understood till here, so that's why this will become very easy for you. So average, tell me what will be average speed for the third case. For the third case, so total distance is not given by the teacher. So first thing is to calculate total distance, which is this is time. So D, okay, D. ST. S is equal to D upon T. So yeah, ST. So over here S is how much? V1 and T is how much? T1. That is how we will get total displacement. This is equal to D1 plus, so D1 is how much? V1 into T1 plus V2 into T2 till the Vn Tn upon total time. So total time is given, which is a T1 plus T2 plus T3 till the Tn. Also over here, this is a infinity. Distance is going till the infinity, and time is also going till the infinity. That's why till here this is enough. Now let's next thing, which is a derivation. Based on derivation, don't get confused between a speed and velocity, average speed and average velocity. Because most of people will get confused. Reason is symbol is the same. So that's why you need to write a word which will be a speed. Symbol is the same. That's why most of people will get confused automatically. Even I will get confused. Yeah. So let me avoid your confusion. here it is saying a relation between average speed and average velocity. Average velocity. What would be the relation between average and speed? Average velocity. So average speed is written like this. V like this. Average velocity, same symbol, ABC. Over here, you will get confused. First thing, which is your distance, could be equal or greater than displacement, mode of displacement. We have seen this thing. So simple for this we have V average. So that's why we can say this average speed. Average speed will be equal or greater than velocity average, mode of velocity average, velocity average. This is nothing but average, but when it comes to this symbol, this is average velocity. Okay, so therefore here average velocity is not becoming greater. Reason is it has a displacement. That this is what is the reason. It has a displacement. That's why it is not becoming greater than average speed. Clear? Whatever we saw relation between distance and displacement, same thing is with the average speed and average velocity. Nothing is different. Yeah, remember apply this mode so that it can't show a direction. Now next note in a note. First we have time average velocity. So if condition, look at condition. If a V is given, but T is a function, V is changing with respect to time, and here we will put value of T, and question is not providing value of T. It means this T is going to function, insert input and get output. If T is a function, then our average speed will be equal to, average velocity will be equal to total time. So dt. So here you can see T is a function. So from T1 till T2, from initial time till the final time, But remember, in this small part, T is a function. That's why we are writing this T1 and T2. Same over here, T1 and T2. Clear? Main thing in this case is limits. What limits will you get? This is main thing. And here question is giving you limits. Not from your side you will take limits. So next we have based on a space average velocity. A space means you can position. So here our function is going to be position. Here position. If V is given and in the V x is a function. value of a b is given, but x is a function. X is a function. Then nothing. Just limits will be different. In the previous case, we saw limits were t because condition was what? Function was t. That's why now here x is a function. So our limits will be simple from x1 to x1 to x2. That's it. So average speed for this case, where x is a function, x is nothing but a space. So this is equal to x1 x2 v into dx upon, I think, total time. So our limits will be same, x1 x2 x1 x2. Okay. Now average speed. Average speed. Average acceleration. Now average acceleration. Look, this instantaneous acceleration, you know, formula is dB upon dt, or you can say A is equal to dB upon dt. Here, if time is not given, then we have one more formula for acceleration, where relation is what? Relation is between a speed and a space, velocity and a space, velocity and position. So you can write it as a b into dB upon dt. It came from here, dB upon dt. Since we are finding a relation between average, not average, velocity and position. So position we are going to take. So dx upon dx. So this dx upon dt is nothing but, it's a formula of a velocity. So dx upon dt can be written as v. Yeah. And whatever left thing you write over here, dv upon dx. You can see this as this instant acceleration is providing relation between uh, velocity and position. So when to use this dV upon dt, and question is when to use this dV upon dt and when to use this v into dV upon dx. And the answer is very simple. I have answered. If you noticed that I said if relation question is providing a relation between v and x, then this is valid for that question. But what if question is not providing the relation between v x, but v upon t, then this is valid for that question. Here in this formula, a is not given. In this formula, position is not given. If t is not given, use this formula. If x is not given, apply this formula. Okay. Let's analyze derivation. Let's derive derivation of what? Of acceleration. Have a look. Derivation based on equation of motion, not based on acceleration. I think based on acceleration, based on equation, based on equation. Equation of motion. You know, equation of motion. Equation of motion. First we have v is equal to u plus at, and second is ut plus half at square, half of at square. V square is equal to u square plus 2as, and one more which is included in this standard is Sn displacement u plus a upon 2n minus 1. First derivation, first derivation, a is equal to dv upon dt. Remember, it's a instant acceleration, instant acceleration derivation. We have two options to derive it. One is simple, and second is by using calculus. Second option is to select calculus. Through calculus we can derive it, and it can be derived very simple without calculus. Okay. You know, if you simplify it, you will shift this dt with a, means multiplication. So dv will become a into dt. Am I correct? Now what is happening? You are able to apply calculus. So this, initially it was a differentiation. A is equal to dv upon dt is a differentiation, but now it became integration. So integration of a dv, integration of a into dt. Okay, dt. Here, from this is nothing but velocity. It insert what? Initial and the final location. Initial and the final location. Upon, and here we have dt. So this will give t from 0 to t, and this v u v u. Try to understand. U is our initial velocity, not location. And V is final velocity. Here we took time, which is from 0 to t, right? Now let's simplify. Since we have limits which are vu 0 t, simplify. Integration of a dv, you know, v. So when you will put this u in place of v, what will happen? So v minus u you will get, which is equal to here. And a is a what? A is a constant, remember, and t is a change. A is a constant. So integration of dt will be, I think it should be t. It should be t. So 0, not 0 but t minus 0. T minus 0 will be t. So a t, a t. And now simplify it. Once you applied integration, your work is to simplify that equation. Here you can see we have final minus initial. V minus u is equal to at. So v is becoming at plus, or you can say u plus at. This is our first equation of motion. That is how you will try by using calculus. Okay, calculus. Now next we have secant. V is equal to ds upon dt, where ds is a position vector. You can say position vector, or it's a position vector, or position of a particle of anything. V, which is velocity, is equal to ds upon dt. How to drive it? I think we are going to take help of calculus to drive V is equal to ds upon dt. V is equal to ds upon dt. Just since you know it's at here, this V is equal to ds upon dt is a depreciation. If you simplify it, what will happen? Dt will go upward. ds will be equal to v into dt. And now you can say this is our integration. This is our integration. Total distance, not the total distance, but the total displacement. We can say position factor. Total displacement. Total displacement. Is it a displacement? If yes, so it should be initial, final. If it is a displacement, then limits would be initial and final. And for this time, 0 from 0 to t. From 0 to t. So initial we have 0 and final would be something. Initial we have 0, final is a t. Final is a t. Integration of a ds will be s, and s minus 0 will be s. Vt minus 0 will be vt. So this. So again we have but integration of dt with respect to t. Integration of look at over. We have value of v, which is a u plus at, into dt, s is equal to this will be as a tu, and integration of dt will be t plus here integration of a t, brother, integration of a t, not a dt. Dt will be t, but integration of a t is nothing but a t square upon 2. Okay, 2. Now here t is a common, ut plus 1 by 2 ats. See, we have brought the second equation of motion, ut t. Here this one more step, so that here this is becoming u dt plus a t dt ut. Integration of dt will be t ut plus a. Okay. For this, here integration of t with respect to dt, this will become t square upon t. That is how I brought this step over here, and then I simplified. Last thing I got this second equation of motion. Second equation of a motion. Got it? Got it? Now third. After this, third. After this, third. Third is third derivation, which is equal to, first we saw v is equal to u plus at, then second we saw s is equal to at plus half at ut. Yeah, s is equal to ut plus half at as well. Third is, which is v square final u square plus 2s. This is third equation. We have to bring this third equation by using calculus. So derivation for the third is going to be a is equal to v into dv upon ds into dv upon ds, dv upon ds. From this we will get, there is a no t, yeah, there is a no time in this. In the third equation we don't have a time, so that's why this formula a is equal to v into dv upon ds came, so that we can find one equation for the motion where there is no time. Now let's integrate it. This is becoming ds. b into dv is equal to a into ds. Integration v from u. This is a velocity. V is a velocity, not an initial and final. Okay, V is a velocity, not an initial and final. So from initial to final, and from zero displacement till the final displacement. Clear? Let's integrate and simplify it after integrating it. So if V is a constant, but you know V is not going to be constant. It's a velocity. So V will be, yeah, it is saying integration of V with respect to dV. And you know, integration of any variable with this same variable will be nothing but x upon n plus 1, or you can say square plus 1. So here integration of this v with respect to dv is nothing but v square upon 2, and limits are u v is equal to here you can't say that a square upon 2. Why? Reason is both are not same. A and s are not same, they are not same, that's why. So a is a constant over here. In this equation a is a constant, and integration of a ds will be ish. So a into ish, and limits are from 0 to s. Am I correct? From 0 to s, a into s. Now let's put this limits. So first of all we will come v square upon 2 minus u square upon 2. Okay, no problem. Here s minus s minus 0, s minus 0 will be s. So finally we will get s. Am I correct? Yeah, you are correct. In the next step is to here we have to simplify this this step for the next step. So after simplifying we will get 2 v square minus u square is equal to s. 2 will go upward, then final would be v square minus u square, which is equal to 2s. One more step, which is v square is equal to u square plus 2s, and you can see this is our third equation of motion, v square plus u square plus 2s. And how to remember? Main thing is how to remember. Once you understand derivation behind equation of motion, it becomes very easy to remember it for the long time, not for the temporary. You know, first is nothing but final dv upon dt. So final velocity will come. So v is equal to u plus 30. Time is for two equation of motion, first and second. So v is equal to u will come, then 80 hour. A is the solution. And you know, all these three equation of motion came from a is equal to b upon t, p upon 2. Okay, then you will put v as a u minus v, not u but v minus u. Am I right? You are right. Whatever we saw derivation, calculus was used. Without help of calculus, we can still derive equation of motion. But you know, we are ahead of 10th standard, that's why calculus was compulsory. Okay, we were saying how to remember v is equal to u plus lt, and second is for the displacement. S is equal to ut plus half radius square, where there is no v. For the third equation, v, which is final, v square, a square will come, v square minus u square. Okay, v square minus u square. Okay. But in right hand side is what? I think 2s, not 2s, but yeah, 2s. Yeah, you can see. So v square is equal to u square plus 2s. We have one more equation for the motion. which is new, not similar, not familiar, not similar, not familiar, which is the ascent. Ascent will be used when question is asking in this second, in this displacement, what is this, what is that, in this time, what is it? For example, in 1 second, what is the displacement? So in this particular time, we have to calculate displacement. Then this fourth equation of motion will be used. Or you can say will be applied. Let's see derivation behind it. Behind it, a derivation. Fourth is ancient is equal to u plus a upon 2n minus 1. I will answer of all the terms that are present in our equation, so that we can use or apply this without having any dots, This is our new equation for the motion. Now we are going to drive it. Statement. First of all, let's see what is the statement. A particle have inertia. So statement is a particle. There is a particle who have inertial velocity u and constant acceleration constant a, then displacement in nth, this word nth, it's not a word, in nth second, you can say. It is asking within 1 second, within a certain second, what is going to be the displacement. That is what is to calculate by using this formula. So in a particular second, not in a particular journey. If you take journey, what will happen? You are taking total time, but case will provide. In some cases, we will see it is asking displacement only in this 2 second, only in this particular second. In that case, formula is going to be different. So this was a statement you can read. Ascent is equal to Sn minus Sn. Look, this first equation came from where? I would say it came from this statement. There is a particle we have initial velocity u, initial, but not final, u, and constant acceleration. Acceleration is constant, means it doesn't mean acceleration is constant. It means velocity, constant velocity is not equal to constant acceleration. Try to understand. Both are not same. They are not same. So acceleration is constant. Let's suppose there is a vehicle, or you can say there is a object which is moving with 2 meter per second raised to power with this much acceleration. That particle is moving with this much acceleration, and it is saying that it's a constant. It's a constant acceleration. Means during the journey, acceleration will be same 2. After 5 minutes, same 2. This is what is the meaning of a constant acceleration. So if acceleration is constant and acceleration is constant, you know that equation of motion is valid when acceleration is constant. Am I right? Equation of motion is valid when acceleration is constant. So yes, that's why it is giving you warning that your acceleration should be constant. Clear? Initial velocity is u of the particle, then displacement in nth second, in 2 seconds, in 3 seconds, in 1 second. But second is very small. Not second, but time is very small. Time is very small. In very small time, what would be particular displacement? So this ascent is nothing but this is a small displacement in a small time, got it? And here ascent means time is how much? Second is how much? 1. Okay, you can put 1. And here previous time was how much? For example, here this is not 1. Let us suppose there is a line who has a timeline. Over here time is how much? T is equal to 1, T is equal to 2, T is equal to 3, T is equal to 4. Question is asking between this time, what is the displacement? So our previous second is what? This is previous. So 2 minus 1 will be 1 second. 2 minus 1 will be 1 second. So previous, this n minus 1 is previous second. Okay. And n is a current second. So this current minus previous will be this part. Final minus initial. With respect to time, this displacement we will get. Okay, got it? From here, you know that Sn is nothing but we have initial velocity which is a u. In particular second. Here you will have to apply second equation of motion. Which is equal to S is equal to ut plus half t square. But in the place of a t, we have second. Just put second. So S is equal to nothing but ut plus half a. In the place of a t, just put n a square. This is our equation number 1. Clear? Equation number 1. Second, this was for Sn. But what about for Sn minus 1? Now, just in place of a t, we are going to put n minus 1. This is the time of a displacement. So in this equation, just put a value for t as n, and in this you have to put value for t as a n minus 1. So u will be as it n minus 1 plus 1, a will be as it n minus 1 raised to power 2. This is our second equation. And now add the, not add, here, this final minus initial, final minus initial. So final minus initial, then your final equation will be this, final. I have told that n minus 1 is nothing but previous second. This is previous second. And n is a current second. Next, you cancel next second. So previous, next, and previous will give between part, between second, or you cancel between displacement. So finally, Sn will be nothing but un plus half a n square, then minus u n minus 1 plus half a n minus 1 square. un plus half a n square minus un minus plus u minus half, and then we have a, here it is n square minus 2n plus 1 square. Okay, you can see this 1 by 2 is cutting, this is cutting, a by 2, here this is I think minus un, so plus un minus un, yeah, finally u, and then we have a. Don't use over here algebraic, okay, algebraic. You know, here we use what is that thing here? We say this 2 will come downward with this variable 2n minus 1. I am forgetting this 2n minus 1, this 2 will come downward and 1 will be upward. 2 minus 1 and 2 downward. If it was a 3 minus 1 and 3 will be downward. And that method, or you can say that rule, is what I don't know name of that rule. So u plus minus will become plus. So 1 u plus half a upon 2, this 2, a will be as it, and 2 n minus 1. So finally we got this thing without making mistake. Finally we got this fourth u, this 4 terms are cutting to each other, u, a as it, 2, okay. Then we have 2n minus 1. That is how you drag any equation of motion. That's it.